Okay, so let me welcome you at yet another research seminar of the GOAT research group. And our today's speaker is Martin Koutecký, and will speak about scheduling of few types of jobs. Okay, Martin, please.
Okay. I thought that you announced that I will be speaking about scheduling goats on a field or something like that, and I'm curious about other goat topics at your seminar. But anyway, so this is a joint work with Johannes Zink from Würzburg. This is a nice story. About a year ago, he came to Homonolo, and I stated some open problem there, and he solved it, and then we worked on it and extended the results a little bit more, and this is the result. As you can see, I'm using his slides. The paper appeared at ISAC last year. I hope that, so the slides are designed to take about 20-25 minutes. I will try to be a little bit slower, and definitely you can ask questions. And then after I'm done with the slides, there's, I think, a very interesting open problem related to this that I would like to discuss in a little bit more detail using the whiteboard. So that's about the plan for me now. So scheduling is an old fundamental task in combinatorial optimization. What is it? So we're given a set of n jobs with individual processing times. So in the picture, you have job P1, which takes 10 units of time, job P2, which takes 7 units of time, and so on. We have m identical machines, in this case, 3 of them. And the objective is to find an assignment of jobs to the machines, which minimizes the maximum completion time, or in other words, the makespan. So for example, this is one possible assignment of jobs to machines. And as you can see, machines 2 and 3 finish at time 17. That's the largest completion time. So that's the makespan. And probably if you shuffled around, you could see that you couldn't do better. So this problem is called PCmax. P is for identical machines. Cmax is for makespan minimization. As we will soon see, there are other models, other objectives, but this is the most basic, most fundamental problem. And it's NP-complete by reduction from bin packing. The reduction is very easy. You replace jobs with natural numbers. These are the sizes of items. We replace machines with bins, each bin of size Cmax. And now we're assigning items to bins, and we don't want any bin to overflow. And so these problems are pretty much equivalent. So the question we are asking ourselves is, how could we restrict or simplify the model so that things become easy? How much can we restrict the model so that things still remain hard? So one idea is, what if we only have few machines? So this doesn't help pretty obviously, because the bin picking with 2 bins is just partition, which is still NP hard. So PCmax, even with 2 machines, is still NP hard. So another idea is, what if we choose a different encoding so we can still have many jobs, but they are only of a few types? So for example, in this case, we have 3 types. Type 1 has length 10, type 2 has length 7, and type 3 has length 12. So the number of types is small, but the job sizes can be large, and the job multiplicities, the n1, n2, n3 numbers, these can be still large. Okay, and we still have these identical machines. So this would be called PHMCmax, where HM stands for high multiplicity encoding. And it turns out that this problem is polytime solvable if K is a constant by a breakthrough result of Gemans and Rotvos from 2014. They were interested in bin packing with few item types, but as we saw, this is equivalent to makespan minimization. So, okay, we have some positive results. So now this refines our question: how much, how could we make the model richer, just a little bit, or maybe more, so that it becomes hard? That's the question. So what are the models we will be studying? So CMAX is that we're looking for makespan minimization, HM is high multiplicity, P is identical machines, and additionally, we will be looking at the uniformly related machines model, where additionally each machine has a speed Si, and a job with length Pj needs time Pj over Si on this machine. So if the speed is S2, it means the machine works, for example, in this case, M2 works twice as fast as M1, and M3 works half as fast as M1. Okay, so you can see in this picture, for example, that the blue job is 4 times as large on M3 as it is on M2, right? Or you can relax this even further into the unrelated machines model, where we have a different processing time for each machine and for each job. So if you want to have a real life example, in Q, you should just think about CPUs of different speed. In R, you should think about CPUs and GPUs. They are useful for different tasks. They're not comparable just by scaling. Okay, so those are the main models I will focus on. And then I need to say something about parameterized complexity. So a problem is fixed parameter tractable FPT in K. K is some parameter. If it can be solved by an algorithm of runtime f of k times poly n, f is some computable function, and n is the input size. It's in XP if there's an algorithm running in n to the fk. And if we show that the problem is W1 hard, that basically means it's unlikely to be FPT. So those are the 3 terms that I will need to describe the results. Okay, so far so good. I don't really, like, if you want me to see you nodding, you should turn on your camera. Definitely, if you don't want to nod and you have a question, please shout. Okay, so it's good. So what are the results? So if we don't use identical machines, already if we use uniformly related machines, so basically the smallest generalization we could make, the problem becomes NP hard with k equals 6 job types. So if you just have 6 job types, you have uniformly related machines, the problem becomes NP hard, even though for constant k, the problem with identical machines is polytime solvable. I will say more at the end about cutting stock. Basically, cutting stock is the uniformly related version of bin packing. So in bin packing, you just have one type of bin that you can use. In cutting stock, you have smaller and larger bins, and they have different costs. So we also show that cutting stock is NP hard with 8 item types. And then we ask about the parameterized complexity. So what if, obviously the reduction we will use here in the first case, and for Q HMC max, the NP hardness reduction, that requires long numbers, both in terms of the job length and in terms of the job multiplicities. Otherwise, there's a dynamic program that solves the problem. I will discuss it a little bit more, but it's not that hard to imagine. You have to basically imagine knapsack and generalize this a little bit more. But maybe you can imagine that if the numbers are not large, you can do some dynamic programming magic. And so what we're interested in is basically, could this dynamic program be improved? Because the dynamic program runs in time roughly n to some function of k, where n is the number of jobs and the job lengths, right? So can this be improved to just function of k times poly n if the lengths are bounded. And we also answer this negatively. So even if the input is encoded in unary and your parameter is k, you can't have an algorithm running in time f of k times poly n, unless fpt equals w1 or something. Okay, and one more interesting result is, so as you saw, Gammons and Oswald showed something about PC Max. Basically what they showed is that if you have many jobs and their length is encoded in unary, then the problem is FPT. But it wasn't known whether if you have unary many jobs, polynomially many jobs, with long sizes, with sizes described as long numbers, whether this is FPT. So we actually show that it is. So that's something, the proof is very simple, but it wasn't known before. Okay, and then we also show these dynamic programs, as I said. So both in the uniformly related machines and unrelated machines, we show some dynamic programs. Anyway, so the agenda is mainly I will talk about the hardness reduction. That's the most interesting part. And then I will talk about how to get this FPT result. So the reduction is we reduce from bin packing. Bin packing is already hard for so-called tight instances, meaning every bin is exactly full. There's no slack. Okay, we reduce this to balanced bin packing. What does it mean? It means that not only is every bin full, but every bin has exactly the same number of items in it. Okay, that's balanced. And from this, we reduce to QHMC max. So the reduction from bin packing to balanced bin packing is quite simple. We need to compute how many jobs of size 1 we need to add. We need to do some, we need to expand the bins a little bit, but the numbers work out and it looks like something like this. So from a tight bin packing instance, we get a tight balanced bin packing instance. Fine. And now the interesting part. So what do we have? We have a balanced bin packing instance. So we have a multi-set of numbers, A1 to AN. We have K bins of size B, and A is our total size of items. The very basic idea is that for item of size AI, we will encode an item of size AI using a machine MI. Okay, so for each item, we have a machine. And this is like on first sight, it might be clear that you can reduce bin packing to scheduling. And there's this obvious reduction that I showed you in the beginning, but that's not the right reduction. We need a different reduction where we transpose items and bins with jobs and machines, right? If we want to show that something is hard for few job types, and we want to start with an instance which is hard for few bins, we need to change the role of bins and items. Okay, so that's something important not to miss here, that we're encoding the items using the machines. It's obvious how to encode items using jobs. It's not obvious how to encode items using machines. So that's kind of the non-trivial thing that we do here. Okay, and we have so we have 6 job types, but yeah, so 6 in the case where K is just 2. Anyway, so we have these job types. I will explain what they do exactly. So beta J is some job and or job type, and if beta J is on machine MI, this is exactly if item AI is in the JF bin. That's what we will encode. So this is the idea that, this means that the machines where we schedule the job of type beta beta 1, those correspond to the items which should go to bin number 1. And then these gamma type jobs enforce that each bin has exactly the same number of items and the same sum of items, the same capacity. Okay, so I will explain now in more detail. So each machine has some speed. The way you should think about the speed really is that each machine has some capacity. And the capacity is slightly larger than some t. Okay, and actually it's exactly t plus ai, where ai is the size of item I, right? Now, beta type jobs are so large that we have at most one per machine. Okay, and because we have m machines and we have m beta type jobs, we know that we will have exactly one beta type job per machine. So this is easy, and the beta type jobs, their size is set such that the remaining capacity on this machine is a times tj plus ai. Okay, so the remaining capacity depends on the item that this machine encodes. Then we have m times a gamma type jobs. Because any machine can execute at most a gamma type jobs, we have exactly a gamma type jobs per machine. Okay. And now there's this nice inductive argument that when you look at, for example, lambda 1, gamma 1, gamma 2, so those are like, so now I just switched to the simplest scenario where I have two bins, in other words, partition. Okay, so I have, what I'm saying is that the gamma 1 type jobs are larger than the gamma 2 jobs. And you can see that the machines which get the beta 1 job have more remaining capacity. And so the numbers just work out so that I really have to put all the gamma 1 jobs on the machines which have a beta 1 job. Okay, otherwise I wouldn't be able to fit everything. And so then I'm left with the gamma 2 jobs. And again, because these are larger than the gamma 3 jobs, if I had more bins, I have to put them on the machines with the beta 2 jobs, and so on. So again, I have this nice invariant that I only have gamma 1 jobs on machines which have a job beta 1. So this fits. So far, so good. And now the the differences between the specific machines somehow have to come in. Okay. So how do we distinguish, or what's the difference between gamma 0 and gamma 1? Those are, so J here, sorry, I'll go back. So here we have like 1 and 2. That would be bin 1 and bin 2. Okay. Here, for each bin, I further refine the gamma jobs to 0 and 1. Okay, 0 is slightly smaller than 1. And again, it works out so that I can put at most AI jobs of type gamma 1j on the machine MI. Okay, this means that I have to put at least A minus AI jobs of type gamma 0j on this machine. And because we have exactly A, that's the sum of all, like the total size of the item, the instance. So we have this many jobs of type gamma 1 in total. So this enforces that MI has exactly AI jobs of type gamma 1j. Okay, so this is a little technical, but I think the idea should be clear that you can set the numbers in this way, and you can argue the invariance so that you really enforce that this happens. And so that's basically the reduction. So here it is kind of all together. You have a job of, or you have an item of size 1, item of size 4, item of size 1, and here are items of sizes 2, 1, 3. And these correspond to the first bin, these correspond to the second bin. The way it's encoded is that the beta 1 jobs appear on these machines and the beta 2 jobs appear on these machines. And then, as you can see, the gamma 1 jobs encode the size of the item. So here we have 4, here we have 2, for example. And this is the only way to put things so that everything fits. Okay. And so to get the NP hardness result, if you have k equals 2 bins, that's partition. That's already NP hard. And because we have for each j, we have 3 types: the beta, gamma 1, gamma 0. We have 6 job types in total. So that's the result. So I will show here already the generalization to W1 hardness. So as you can see, you know, if we had a hardness of balanced bin packing for more bins, parameterized hardness, then everything goes through. And this hardness exists. There's a paper by Janssen and others from something like 2012, 13, or something like that, which shows that basically you cannot solve bin packing faster than n to the k if you have k bins and if the items are encoded in unary. So if you reduce from that, yeah, okay, so what I wanted to say is this. So the size of the jobs, the beta jobs are the largest, and their size depends on the total size of all items, this capital A. Okay, so if the capital A is large, then the beta jobs, at least the beta jobs will be large, but if the total size of the input instance is bounded, then you can see that all the sizes of these jobs will be bounded, so that's fine. And then the multiplicity, so the beta jobs, there's not that many of them, but the multiplicity of the gamma jobs is large. It depends on the total instance size for the balanced bin packing, depends on the capital A. So again, if the capital A is given an unary, then the multiplicities of these jobs will be bounded, it will be encoded in unary, and everything works out. So that's the hardness reduction. You know, what we used in the reduction from Q, from the uniformly related model, basically was that the capacity of each machine depended on the item AI, right? Each machine had a different capacity. Speed is almost the same as capacity. And so if you can model capacity somehow else, then you're fine. So basically for the unrelated machines model, we do some tricks to block out exactly the right amount of capacity for each machine, and then the reduction goes through. So the proof for our HMC max is almost the same. I will say more about this reduction later, and then the parameterized hardness I already explained. And then one more thing I want to say about hardness is other interesting objectives are, for example, the L2 norm of the schedule. So what does it mean? You can look at each machine and what time it finishes, right? Makespan is minimizing the maximum of these numbers. The maximum is the L infinity norm. you could also minimize the L2 norm of this. So basically, you're allowing some machine to finish earlier and some machine to finish later, and you're not really just checking the maximum, but basically the more you differ, the more punishment you get. So this also appears in literature, and for many, we extend a lot of these results to L2. And then another fundamental objective is the sum of weighted completion times. So this is basically every job, when it finishes, it contributes its weight times its completion time to the objective. And this behaves somehow quadratically, but it's a little more intricate than this L2. And so some of our results extend to sum of weighted completion times, but it's a little more difficult, and we weren't able to extend it as much as L2. So that's the hardness. Okay, so any questions about the reduction? Okay, so I'll go on. So this part will be shorter. So now I want to argue that PC max is FPT parameterized by the number of job types K. Now note that I don't have the HM, the high multiplicity version here. So the number of jobs, like you can pretend that each job is given individually, right? That's something I will want to exploit. Okay, so the proof idea is this. So the algorithm of Gemans and Rotvos has runtime log Pmax. Pmax is the longest job size. To some f of k, this is actually a double exponential in k if you were interested, times polylog n is the number of jobs. There's a simple inequality which gives you that this thingy is FPT, it's just some function of k, times Pmax to little of 1 times polylog n. Okay, so this is FPT if Pmax is small. But we're interested in the case when Pmax is large. So what do we do? There's an algorithm of Franken-Tardoš from 1987, which basically, if you have a vector of numbers, and you should think of it as a hyperplane, okay? And this, so the hyperplane somehow has high complexity. It uses large numbers. It has a very long encoding. So their question is, can you round the numbers? Can you tilt the hyperplane just a little bit so that it behaves exactly the same with respect to the integers, right? So you will move the hyperplane, and some point which was on the left now is on the right. That's fine, but you don't want this to happen for any integer point, okay? And they give an algorithm to do this, and they give bounds on how well you can do this. And basically it says, if you're interested in the hyperplane behaving correctly on a bounded box, then you can do it with such and such accuracy. And the box here is bounded in terms of n, the number of jobs. And as I said, this is given in unary. Okay, so this vector p is like this hyperplane I was talking about, and they give us a different vector p bar, which behaves exactly the same with respect to all numbers or all like job multiplicities up to n to the k. Or sorry, if the job multiplicities are up to n, then the numbers in p bar will be bounded by n to the k. Sorry, so that's how much we reduce the complexity of the hyperplane, right? So the hyperplane initially was encoded by like arbitrarily long numbers, but if we know we're in a small box, we will get an equivalent hyperplane, and the numbers appearing in this will be at most n to the k. So what we get is then that, you know, this Pmax gets replaced with n to the k, and that turns out to be fine because there's actually a little O of 1. Or in other words, you can plug in n to the k here into Pmax and into the first expression of the runtime, and you see that log of n to the k is just k times log n, and so we get, you know, k to the function of k times n, times log n to the function of k. That's what we had before. So basically, it's enough to use Frank-Dardoš to reduce the processing times, but you need the assumption that there's not that many jobs. Okay, so what's the summary of our results? I'll give you the whole table. So for Cmax, it's polytime for constant k, that's Gaiman-Ratvos, and then the red and green results are all ours. So for Q and R, we have NP hardness. For Cmax, also for L2, and for sum of weighted completion times, we were only able to do it for the unrelated machines, but not for the uniformly related machines. And actually, do you actually see my mouse? Yeah, okay, so these boxes are, I think, one of the most interesting questions in scheduling, because there's no analog of the algorithm of Gaiman-Ratvos here, how to deal with these functions as opposed to Cmax. I actually believe that at least L2 should be polytime, but I tried showing that a few times, and it's not easy. Okay, what about here? So we have FPT for so this other half of the table is the non-high multiplicity versions, right? So for identical machines, we have FPT. Again, nothing is known here. And we have XP results when one of the numbers at least is given in unary. So either the job lengths are given in unary or the job multiplicities are given in unary, then the problem is XP. We have some dynamic programming or turbocharged dynamic programming algorithms. And then again, we have these hardness results, which are the same reduction as here, just from the parameterized hardness of bin packing. And so to close with some open problems, everything that's a question mark in this table is a good open problem. Another question is, you know, you could try to improve the numbers. So the best we can do here is for unrelated machines, k equals 4, we know it's hard. I think there's a result saying that for k equals 2, it's not hard, but I'm not sure. And so you could ask, you know, what is it for k equals 3? I don't know. I think the biggest question in parameterized complexity of scheduling is just, okay, is identical machines, high multiplicity, makespan minimization, is it FPT in terms of k or not? So what we know now is if either the job lengths are given in unary or the job multiplicities are given in unary, then the problem is FPT. But it's not clear whether both can be long numbers. Maybe you could look at more like other scheduling models where you have release and due times, or you minimize tardiness. There are many other objectives. And then this is the problem where I want to say a little bit more about it. So give me a second. Let's see if I can reconnect. Okay, good. So, okay. So now I want to say a little bit more about the cutting stock problem. So what's cutting stock? So in cutting stock, you have you know, m bin types, each bin type has a capacity, and it has a cost. Okay, so the capacity is maybe Bj and the cost is Cj. So it looks a little bit like the unrelated machines model, because thinking about machines with different speed is like thinking about bins with different size, different capacity. And that's so okay. So I will now tell you how to like what's an integer linear program model for QHMC max. This will tell you how to reduce from QHMC max to cutting stock, which is how our NP hardness reduction works. And then the open problem is we have W1 hardness for QHMC max. And I have some indication that this, like, you would need to invent something completely different to show W1 hardness for cutting stock. Okay, there's something weird going on with cutting stock. On the surface, it looks very similar to QC max, but actually it seems to me that it behaves very differently. So before I go on to this reduction, I want to just highlight what's the question I'm asking here. So is cutting stock W1 hard parameterized by k number of item types? Okay, so we have m bin types, and we have items of sizes a1 to ak, and there's n1 items of size a1, and so on. So again, we have item sizes, item multiplicities, and we want to place and we have some total budget b. Right, so the question is, can I pack all of these items and buy bins of total cost at most b? So is the question clear here? So W1 hard, parameterized by a number of item types if everything in unary. Okay, so here the item sizes, the item multiplicities, the bin costs are given in unary. My question is this W1 hard? Okay, actually, even what if, so we know that if you allow all of these numbers to be long, the problem is NP hard. So I would be happy with showing that it becomes that it's W1 hard, even with one of these aspects being in unary. So what I mean by aspects is you have the item sizes, you have the item multiplicities, and you have the bin costs. So these are the long numbers. My question is, can you make one of these unary and all the remaining ones are still long? I would like to show that this is W1 hard, and I'm not able to do it. Okay, so that's the question. And so now, how to encode Q Cmax as an ILP? There's a very simple model. So I will have a variable xij, which is the number of jobs of type j on machine I. Right? And I have two types of constraints. So the first is all the jobs of type j have to be on some machine. Okay, so when I sum across all the machines, I have to sum up to nj. So that's the first type of constraint. And then the second type of constraint is the total length of jobs that I scheduled on machine I has to actually be able to fit there. So xij times pj over si. Now I sum over the job types. This has to be at most Cmax. Okay. Now, if I rewrite this, or if I tell you what the matrix looks like, it looks something like this. You have a bunch of identity blocks for the first type of constraint, for each machine 1. Okay. And then you have just one row. This is called a knapsack constraint of these numbers. Basically, it's the vector of processing sizes scaled by the speed, but that doesn't really matter. Okay, and so what's important here, the number of these constraints is just k, but the number of these constraints is m. Yeah, so there's many constraints of the second type, and there's few constraints of the first type. Okay, and so the way our reduction from QCmax to cutting stock, how it works, is that we use the bin costs to basically encode all of these constraints. So the idea is this: when you look at a column in the constraint matrix, and you have m constraints, you can actually look at it as a number of length m in the correct basis, right? So these, let's say that the rows only had zeros and ones, then it would just be a 0, 1 vector of length m, and that's like an m-bit number. Okay, this is more or less true. Now, if you were summing up these numbers, and somehow I could guarantee to you that there is no carry, then you can express all of these constraints with just one constraint, but using very large numbers. Okay, so basically, if I don't do it in base 2, but in a large enough base, I can ensure that there is no carry, and I can replace all of these constraints with a budget constraint, with just saying, the cost of the bins will be at most blah, and then by adding some placeholder jobs, placeholder items, I can ensure that actually I will need exactly this capacity, and so I will need exactly this cost. And this way I can model that, I will design a cutting stock instance, and I will be able to ensure that every bin type gets used exactly once. So this is really important. Okay, so in our NP hardness reduction, every bin type gets used exactly once. Now, the problem is when I try to do the W1 hardness reduction. Okay, sorry. So now I will tell you what's the difference between the ILP formulation for Q Cmax and for cutting stock. Yeah, so for cutting stock, basically, you also have this constraint that every item has to be placed in some bin. So you basically have this type of constraint too. So now I'm not being exact, but this is morally correct. So try to bear with me. But then you don't have these constraints you don't have, and instead you have some objective function. You have some min something. Okay. So basically the ILP has some fairly complicated objective here, but it only has k rows here. And the problem is this: there's a result by Aliyev and some others from something like 2018 or so about ILPs. And the result says that there exist sparse optima to ILPs with few rows and small coefficients, let's say. So I'm not going into the details, but what they imply for us is that if the bin sizes are bounded by delta, bin sizes and item sizes, okay, are bounded by delta, then there always exists an optimum using at most something like log delta to the k, I think, bin types. Okay. So what we crucially use in the NP hardness reduction is that we can ensure that each bin type gets used exactly once. And what we have here is that if you restrict the numbers, you cannot do this. Like, we know for a fact that there are optima that only use relatively few different bin types. Okay, but not few enough that we could exploit this algorithmically. But somehow you would have to find a very different reduction than what we use in QCmax, because as you saw, we used the mapping between machines and items. And now if somehow, you know, I can put into the instance many different bin types, but I have no control over, like, I know that most of them will get ignored, but I don't know which will get ignored. So this is somehow a fascinating question to me, because on one hand, I can't prove the hardness, and on the other hand, the positive result would also be kind of striking, because the best we can do now is by Gemans and Rotvos when you have a fixed number of bin types. So if you have a fixed number of bin types and a fixed number of item types, then you can solve cutting stock. But if you make the number of bin types variable, basically the result of Gemans and Rotvos doesn't tell you much, because there's so much brute forcing involved that you can't use it. So the positive result would be a big algorithmic step, and the negative result would need something completely different. So I think this is a fairly interesting open problem, and yeah, that's all I wanted to say.
Okay, so I believe we can unmute ourselves and clap for Martin. Okay, guys and girls, questions? Maybe let me ask a sloppy question. This last result you mentioned of Aliyev and others, is this also some polyhedral combinatorics? Is this Gemans and Rotvos?
Right, so they are, yeah, I don't understand the result inside. I
Fair
think, but I think it's actually relatively close to, you know, the graver bases or circuits or like this kind of technology, because okay, so I'm kind of making things up here, but so if you it's fairly easy by standard LP theory to show that you know, LPs have sparse sparse optima. So if you have an LP with k constraints, then you will have an optimum of support of size k. And now, using the fact that the ILP optimum has to lie in a vertex of the integer hull, you can decompose the difference between the LP optimum and the ILP optimum into circuit steps, let's say. And because there's few of them and they have small support, I think that's the idea behind it, right? So it's not obvious that there is a few of them because the standard reduction will give you, the standard decomposition uses dimension many elements. So like the first thing you would try would not work. But basically, I think it's like, yeah, you have to use some known results about the circuits of this matrix and so on. And the fact that LP itself has sparse optima, and then getting from the LP to the ILP optimum doesn't mess things too badly. Something like this.
Okay, thanks a lot. Any other question? No, it seems it's not the case, so you can thank Martin yet again, and this will be it for today. Okay.
So what's the GOAT business?